first session of the day. This is a session on post-quantum cryptography. Can we load the slide, please? Fun fact, this is the session with the most authors. We have on average 7.6 authors per paper, so a lot of names to read. So yeah, let's get started. So the first paper is titled Merit, Efficient Post-Quantum Signatures from Min-rank in the Head. It's a paper by Gora Ach, Stefano Barbero, Emanuele Bellini, Andre Esser, Luis Rivera Zamaripa, Carlos Sana, Javier Verbel, and Floyd Zweidinger. And Floyd will give the talk.
Yes, thank you very much for this kind introduction. Let's directly start. Perfect. Yeah, as you probably all know, all currently deployed publicly cryptography will be broken by large enough quantum computers. So there's an urge to replace those schemes with something new. That's why there are currently multiple ongoing NIST calls for new cryptographic primitives, for chems, for signatures, but also for lightweight symmetric encryptions. And obviously we want that those schemes are secure too, but additionally to that we want to diversify the landscape, so we want no schemes based on ideal or structured lattices. And that's why we are proposing Mirith. Mirith is a CMA secure signature scheme based on the hardness of the min-rank problem. Its approach is to use the MPC in the head paradigm, where an MPC protocol is utilized to verify the shared solution of the min-rank problem. Then a zero-knowledge proof of knowledge is extracted, which is then via the Fiat-Shamir transformation transformed into a signature scheme. That's like the basic information you need to know, and that's best summarized in the following table. So here you see the parameters for the category 1 parameter sets. As you see, we propose multiple parameter sets, fast and short, which have signature size from 7.8 kilobytes down to 5.6. Public key size and keygen are rather small and fast, but signing and verifying can be done in around about 5 million cycles on a modern Intel CPU with AVX2 enabled. And the rest of this talk will be following the title of the paper, Efficient Post-Quantum Signatures from Min-rank in the Head. I will first talk about min-rank, what's the problem we are basing our signature scheme on. Next, I will talk about in the head, what's MPC in the head. And last but not least, I will talk a little bit about efficiency. Okay, the min-rank problem. The min-rank problem, given k+1 matrices, M1, M0 to Mk, and an integer r, it's asked to find a linear combination of those matrices which have rank r or below. And this linear combination is represented with a vector alpha from alpha 1 to alpha k. And the cool thing about this problem is it's actually NP-hard, and it's around in the cryptanalytic community for quite some time, so over 20 years, where it's used for attacks against multivariate crypto and decoding code-based crypto. But in this talk, I will use a slightly different modeling of this problem, namely the Kipnis-Shamir modeling. And you see I renamed this big linear combination of all these matrices now to M alpha. And in this Kipnis-Shamir modeling, there exists I need to say that for easier reading, I colored all public information green and all secret information or information we want to attack as red. So in this Kipnis-Shamir modeling, there exists a matrix K such that our M alpha times some identity part and the secret matrix K is equal to 0. And the important part here is this is equivalent to a solution in the min-rank problem. So if you find such a matrix K, you have directly your alphas such that the linear combination has rank R or below. And now we split this matrix M alpha into a left and the right part, where the first n minus r columns are moved into M alpha left or L, and the remaining r columns are moved into the right part, M alpha r or right. And now we can rearrange this equation to what you see on equation 1.3. So M alpha L is equal to minus m alpha r times k. And again, it's important to remember that when the knowledge of the min rank solution alpha is equivalent to the knowledge of the matrix K, such that this equation holds. And as it seems like we didn't achieve much because we plotted up our secret alpha by an additional matrix K, we now have a linear equation. A linear equation which is easy to verify if we found a solution or if we have a solution or not. And that's very important for the MPC protocol in which this is now verified. So a multi-party computation protocol exists of multiple parties, in this case, let's say 4. All parties have a public function f and an image of this function z, and also they share shares xi, which sum up to x. And the goal of this protocol is now to verify if those parties really have a share of this x, such that the sum over the xi's is x. And the protocol accepts if the PIs, so the party members, think they do share the solution, or that it rejects if they think they do not share xi's, the correct xi's. And obviously we want some properties to hold. The first one is we want a low false positive rate, such that we do not have to repeat this protocol too often. And secondly, we want that no information on xi is leaked to any other party, pj. So we want a zero knowledge property. In the case of mirror, this now looks something like this. So we have our solution alpha to the min rank problem m0 to mk. And now we compute additional shares, additive shares alpha I, which sum up to alpha, and the same for our matrix K. Now each party gets its own share, and in the end we want to verify the Kipnis-Shamir modeling, hence I introduced it. So we want to verify that alpha K is indeed a solution such that m alpha L is equal to minus m alpha R times K. And the protocol should accept if this is true. And obviously we want that no information on alpha and K is leaked to any of those parties. Now we are given such a protocol. Now we want to construct a zero knowledge proof of knowledge, in which a prover wants to prove to a verifier that he has indeed a knowledge of a solution to the min rank problem. And this is done by, well, first the prover prepares his additive shares alpha I and Ki and commits on them. This commitment is sent then to the verifier, which first samples the first challenge R, which introduces randomness to the protocol. With this R, the prover then simulates the MPC protocol, commits on certain auxiliary and internal values, which are then sent to the verifier, which samples the second challenge I star, and now the prover reveals all auxiliary data or internal views of the parties PI except for the PI star party, and sends this information to the verifier. This verifier can now recompute all the commitments, check if they are correct, and additionally can check if this MPC protocol indeed accepts the solution to the min rank problem. And in the last step, we now apply the Fiat-Shamir transformation to get the signature scheme. I now do not want to talk too much about the internals of this protocol, as I think this was done quite often, also at this conference. I want rather talk about performance, the efficiency. And as you can imagine, in this protocol, you need a lot of matrices, you compute a lot of matrix multiplications, hence this is the bottleneck in this protocol. And as a matter of fact, 50% of the computation time is simply done by computing matrix multiplications. And these multiplications are based on field multiplications, and therefore I want to talk about a newly proposed field arithmetic for the x86 architecture, especially for the AVX-enabled x86 architecture, to improve the performance of mirrors. In mirrors, we have the base field f2 to the 4, so f16, which is identified by the following polynomial ring you see on your on the slide. And obviously, the goal is now to compute z equal to a times b, and a and b are polynomials of at most degree 3. So I can rearrange this formula a little bit to compute this polynomial multiplication, and the only thing I did here is rearrange the parentheses to the right side, right? So ai are now the coefficients of a, and I simply included x to the power of I to the b side of the equation. I think this is better visualized on the following slide, where you have on the top row you have our polynomial a, and the bottom you have the polynomial b, and the 4 different coefficients of our polynomial. And now what we want to do is we want to first compute a0 times b, well, x to the power of 0 times b, but that's b. Next, we want to add to this intermediate result a1 times x to the power of 1 times b. And after we accumulated all these intermediate results up to a3 times x to the power of 3 times b, we have the solution of the full multiplication. And now, okay, we have a single multiplication computed, but actually we want to do this like in parallel. We want to use vectorization engines of the modern CPUs. So we want to do like 64 of those multiplications in parallel in an AVX register. So you now see these dotted boxes around our polynomials. These are now single registers, AVX registers, 256-bit wide. And we want to repeat this 4-step algorithm to compute 64 multiplications in parallel. And I should mention at this point that I'm only talking about Intel, because on ARM architecture, this whole process is not needed because they have a carryless multiplication. So we don't need such shenanigans I'm showing here. Yes, to better understand this, I will now zoom into this red box you see on the bottom right corner. It will become clear in a moment why I choose exactly this, but to make it everything easier, I will now zoom into this. So we want to compute a3 times x to the power of 3 times b. First, we need x to the power of 3 times b. This can be done with a simple table lookup, which luckily Intel provides an instruction for, the so-called vectorized packed shuffle byte instruction, or VP-SHUFB, I don't know, which takes two arguments, a table and an index. So, and it returns the element within the table at index p. And the important part here is this is done like this is an AVX instruction, so this is done for 32 different b's. This table lookup is computed, and we can compute this table for all possible values of b. So we first compute 0 times x to the power of 3, 1 times x to the power of 3, and so on, up to 15 times x to the power of 3, but obviously we need to identify 15 as a polynomial. I'm abusing here a little bit the notation to make it more readable. And then the output of this function is exactly what we need. And now in the second step, we want to compute a3 times the output of this table lookup. And we need to remember that a3 is a binary coefficient. So it's meaning it's either 0, then this whole multiplication is 0, or it's 1, then it's simply the output of the previous step. So logically written down, it's either 0 or the output of the previous function. And again, Intel provides us with an instruction exactly for this problem called the vectorized packed blend vectorized byte instruction, which takes 3 arguments, a, b, and a mask m. And whether m is 0, either a or b is returned. And again, remember, this is an AVX instruction, so this mask selection process is like done in parallel for 32 different masks m. If I now replace the values with the inputs for our problem, so a is 0, the second input, the second argument to the function is x to the power of 3 times b, and our mask is A3, you see that this whole thing acts exactly as we want it. So 0 is returned whenever A3 is 0, and the table lookup is returned always else. Now we repeat this process not just for A3, but for A0, A1, A2, accumulate the intermediate results, and we got a full multiplication which computes 64 field multiplications in parallel. This yields overall an improvement in the instruction count of 11.5%, which translate to the following table. So on the table you see the two min-rank based submissions to the additional call for signature schemes by the NIST, Myra and Mireth. And additionally, for better comparison, I added Sphinx Plus, the hash-based signature scheme, or the new standard. As you see, Myra yields the best signature size. So the fast parameter set is roughly half a kilobyte smaller than Mireth. In a short setting, it's only 100 bytes, sorry. Public key size is rather identical. And now the big difference, why I'm giving this talk, is like we are 8 to 9 times faster in signing and verifying compared to Myra. But note that Sphinx Plus yields the best verifying times. And also note that when we are switching from the fast to the short parameter set, you see that like the timings, the difference between the timings of Myra and Mireth don't get that extreme anymore, which comes down to the fact that the hashing is now the main part of the computation. So you need more catch-up calls, which are by far the most expensive part now. And with this, I can say thank you very much. The code is publicly available on GitHub. The paper is also on ePrint. Thank you very much.
You have questions? Yeah.
Yes. Thanks for a very interesting talk. I have actually 2 questions. So you mentioned that roughly 50% is arithmetic matrix multiplication. I know that MPC in the head usually also has quite a large chunk of hashing for like tape expansion. Can you give a number for this?
The other 50%.
Okay. And the other question is, if I remember correctly, Intel does have a carryless multiplication instruction, yeah?
Yeah, but only AVX 512. And,
okay.
And there is also a carryless multiplication, but for 64-bit polynomials, which, please correct me, I think is in the BMI instruction set. I'm not 100% sure. Sorry? Oh. And that's simply slower because you have like 64 bits and not 8 or 4.
Okay, thanks.
But yeah, just to get it, like we also have the AVX 512 implementation, and obviously that's quite faster because you have like the carryless multiplication as in Neon.
Do you have more questions? I have a question. So if I understood correctly, your arithmetic, you're multiplying 64 things by 64 independently other things. Yeah. But when you do matrix multiplication, usually you're multiplying like a lot of things by the same element. So is there nothing to be gained by doing
yeah, that's the reason. That's the second reason why Mireth is so much faster. We don't do this. We fully load the matrices into the registers and do a full matrix multiplication only on registers. We don't load single elements.
Right, but I mean,
so the row and the column, and let's go.
Yeah, but you want to multiply an entire column or entire row by the same element, right? So if you just, instead of implementing arbitrary multiplications, implement like a subroutine that multiplies like an entire vector by one element.
It's still
Could this be better? Oh, okay.
Still faster. I can say it. I stole obviously your code from the all-in-vinegar improved parameter sets paper, and this one is faster.
Okay, cool. Thank you. Also, I think for the NIST competition, you're merging with
yeah.
another scheme, right? So can you reveal anything? What's going to change or what's going to stay the same?
Yes. So we are merging with Myra, as the two submissions are super close to each other. The only difference is the internals of the MPC protocol, which I didn't talk about. But we are switching the protocols again, and I think we are coming out at signature sizes of 2.6, 2.8. But the implementation still needs to be done. It's in work in progress, but needs to be done.
Okay.
Yeah, thank you for the talk. So you compared the performance with Sphinx. Have you compared it with dilithium? So regarding efficiency? So.
Yeah, no chance. Lithium is still unbeatable. Where is it? 300 cycles, 300,000 cycles for AVX2. Yeah, we had, what did I say? 5.2 million, so factor 10.
Okay, if there's no more questions, we can thank Floyd again. So the next paper will be about Hete, shorter lattice-based Fiat Shamir signatures, and the authors are Young-Hee Hyun, Young-Min Cho, Julien Deveve, Tim Gunesu, Dong-Young Hong, Marcus Kraus, Georg Land, Mark Muller, Damien Stellet, and Mingyun Yi, and Georg and Julien will give the talk.
All right, thank you for the introduction. And thank you for trying your best to pronounce all the names. That's very appreciated. So Hete is basically dilithium's little cousin that we submitted to the South Korean post-quantum competition. It's one of the 4 signatures that advanced to the second round. And while we were at it, we also submitted it to NIST's additional PQC round, despite them not really wanting any more structured lattices for the signatures. You can find all submission packages, specifications, and more details on the website of the signature. And when I say that it's dilithium's little cousin, that's because they are very similar. It's just that their goal is slightly different. So our goal was to take dilithium's framework and see how much we could shrink the signature size, which resulted in a signature which is not as implementer-friendly as dilithium, which is maybe something I should not say at CHES audience, but here we are. This is done by doing 2 main changes, which are the distribution of the nonce, which is now continuous, it's uniform in a continuous hyperbole instead of the hypercube in dilithium. And the response is computed in a so-called bimodal form, but more on that later. And the thing is, when you shrink the signature size, it means that you get more security for your scheme. So what you can do is actually lower the overall dimensions of your scheme, which means that we are doing less arithmetic operations in Hete than in dilithium. So to compensate, we allowed ourselves to increase the number of repetitions in the scheme, which is also helping us to reduce the signature size. In the end, we are saving for level 2 more than about 1,000 bytes, and this allows the signature to fit in a TCP packet, which is, it has some good use cases. So I'm going to give you a bit more cryptographic background, and then I will hand over the talk to Georg, who will tell you about his time implementing the scheme. So first, as you all know, I think, dilithium and so Hete are based on the Fiat Shamir with a board signature framework, which turns a Sigma protocol into a signature. And I'm going to detail the Sigma protocol we used, which is very similar to dilithium. So in a Sigma protocol, you start with a prover and a verifier which share a public matrix A. And the prover has a vector S, which is essentially ternary. And this vector, and the verifier only knows the image of this vector by A, so the vector T. And the goal for the prover is to prove that it knows S without revealing it. This is achieved by sampling a nonce, which in our case is uniform in some hyperbole with small radius, and committing to it with the W vector you have here. we are rounding y because it's a continuous hyperbole, so we don't want to deal with real numbers. The prover is getting back some binary challenge. It was ternary in dilithium, but we are going with binary for technical reasons. And then with some probability, you answer with the response Z, it's Y plus SC, or you have to restart your protocol. Very close to dilithium for now. Then the verifier will be convinced if some equation is satisfied, and most importantly, if the norm of Z is small enough, because it's comprised of Y, S, and C, which are all very small polynomials in terms of Euclidean norm. If you do the rejection sampling correctly, then you reveal nothing on your secret, which is the main issue. And also, if you do not know S, you are unable to convince the verifier without breaking either the module SIS or module LWE assumptions, which is also, they are exactly the same assumptions as in dilithium, so very, very close. I was talking about bimodal form. What I mean is that what we actually do is during the response phase, we actually change the sign of SC with probability 1/2. So either plus SC or minus SC. This creates a few problems because the verifier needs to still be able to verify at the end. So we are making a few changes. Mainly, the main one is that we are working mod 2 times Q. And then we slightly change the public matrix A and the secret S to A prime and S prime, as you see on the right. This consists in introducing some kind of trapdoor in the first column of A. And if you do the matrix vector multiplication, you see that you end up with Q times J mod 2Q, and J is, it's a 1 and then all zeros as a vector. And the nice thing is that this vector, it is equal to minus itself mod 2Q, since Q is equal to minus Q mod 2Q. And so it means that the verifier is now still able to do verification with this updated verification equation, and it doesn't matter the sign it chooses for QJC. It's also independent of the sign chosen by the prover. And then we still have the same nice properties. If you do rejection sampling correctly, then everything is fine. If it's still hard to convince V without knowing the secret. So we can compile this Sigma protocol into a signature scheme by applying Fiat-Shamir. And this gives you this kind of blueprint where the challenge is now sampled using some hash function on input, the commitment and the message you want to sign, and you restart until you get a signature, right? And the most important parameter actually in the scheme is the bound for the Euclidean norm, the bound gamma, because everything depends on that. You have to set gamma large enough to get correctness, but you want to make it small because the smaller it is, the harder it is to forge. And if you make it smaller, you can still keep correctness at the cost of increasing repetition rate by being more picky on the Z you keep. So this gamma is very important, and also it is basically this parameter that tells you how big your signature is going to be at the end, because smaller gamma means smaller Z, so less encoding to make. So the reason why we chose hyperboles is for this kind of virtuous circle. We were trying to minimize this gamma parameter, which means that you have a smaller signature size, you have more security, so you can decrease the dimensions, you can decrease your parameters, which results in even smaller size, etc., etc. And you have a theoretical analysis that we did a few years ago, which says that choosing hyperbole uniform distributions is the best choice you can make if this is the goal you're trying to achieve. You had other propositions that were made, but they usually aim for a different kind of compromise. There is one last important piece missing to the puzzle here, and it is the rejection step. So picture what is going on. So you sampled your nonce Y. It is somewhere in this in any of these big circle, and then you shift it with plus SC or minus SC. So your final response Z, it is uniformly distributed in either of the two white circles. To make sure that Z is not leaking anything on S, on the secret, you would like it to be uniform in the colored circle in the middle. So how do you do rejection sampling? Well, if you are outside of this circle, then you're going to reject with probability 1, so always, the vector Z. And if you are inside the colored circle, there is actually a tricky part, which is in the middle, the blue part, it is where the two hyperballs are overlapping. So elements there, they are overrepresented. So to compensate for that, you have to flip a coin and keep them only with probability 1/2. But how do you know in which region you lie? You can actually compute two Euclidean norms, or just squared Euclidean norms, not even need to do the square root. The first one is, of course, the norm of Z, which tells you if you are in the colored ball or not. And actually, if you look at the norm of 2Z minus Y, if it is very long, then you will know you will be in the purple region on the left. If it is short, you will be in the blue region and need to flip a coin. And you actually are never in the translucent purple part due to the way Y is sampled, and it's in the left hyperbole. This works whatever sign you choose. There are many other optimizations in the scheme that I don't really have the time to talk about now, but the main one is that during key generation, we also introduce a way of doing rejection sampling on your secret in order to drive gamma even smaller. And as in the lithium, we are truncating the public key and the signature, which introduces well, some technical issues that you have to solve by updating the way you compute the commitment and what you hash, etc. But we'll skip that for today.
Yeah. Thanks. Yeah, so I'm going to talk about implementation considerations. Also, this is a picture of Markus and me first trying to understand what's going on. So with respect to the lithium, what changes and what challenges do we have? And most importantly, we work over a 16-bit modulus. So the value Q is a 16-bit modulus that makes things easier for storing polynomials. So we can store polynomials more efficiently than the lithium. So regarding challenges, we also, as you might have noticed, we also introduced quite a few new modules that you have to implement. So first of all, we have some fixed point arithmetic during signing and also during key generation. During key generation, especially for the complex FFT that's required for rejecting over the secret. But on a good note, so Julien said we are moving to computations modulo 2Q. That's the theory part. In practice, you can do almost all computations over Q. That means, so Q is the 16-bit modulus, so you can stay within this 16-bit prime field. And yeah, so except for some small operations like rounding, you will have to recover like the 2Q representation. And the most important change or the most important challenge is you can see when you do a profiling of Hette the hyperbole sampling. Yeah, so signing during signing, 85% of the cycles go into hyperbole sampling. That's even already for the AVX2 implementation. And yeah, another small spoiler. So also in our AVX2 implementation, the complex FFT is not yet fully optimized, and still it's like 25% of cycles going into there. So hyperbole sampling, that's our non-sampling, and for the lithium, you might know non-sampling is quite a simple procedure. Yeah? It's just you take a shake 256 output and you parse the bit strings into signed integers. So it's really trivial, yeah? And with that in mind, we're going to talk about hyperbole sampling, which is much more complex. What happens there is, first we need continuous Gaussians. and we need quite a lot of them. So n is the polynomial degree, 256, and k and l are the module ranks. And we need 2 more samples with a standard deviation of 1. And then we compute the L2 norm of this vector, and then we drop 2 samples and divide the remaining samples by the L2 norm from above. So every implementer will now ask, wait, what? Continuous Gaussians, not even like discrete Gaussians, what we're used to. And actually what we're doing is we're doing continuous, or we're doing discrete Gaussians with a huge standard deviation, which approximates continuous Gaussians with a small standard deviation. Then those 2 steps, normalization and dropping the coordinates, happen, and afterwards we even go back. So we are doing a discretization step, and then we have a fixed point representation of our nonce y. Okay, then the next question is, how do we actually sample a discrete Gaussian with a huge sigma? And that's actually a more or less known technique. So we start by with a discrete Gaussian with a small standard deviation sigma, or let's say a somewhat small standard deviation of 16. That's done by a CDT sampling, so we have just a pre-computed convolutional distribution table. That's also a very easy, quite easy procedure. Then we add 72 uniformly random bits as our LSBs, and that's obviously not a discrete Gaussian then, so we have to do a rejection step on this sample candidate. But with that method, actually the rejection probability is quite small, like 2 to 3%. But for the rejection, we will have to approximate an exponential function with a quite good precision. Luckily, we found a nice solution for this via Chebyshev approximation. And you can see this procedure is highly performance critical because it's repeated. Obviously, for each hyperbole, we need n times k plus l plus 2 Gaussian samples, as I said before, but then the repetition rate kicks in, so it's again multiplied by 6, so on average that's about 9,200 times repeated for HT2 on average. Yeah? As you've guessed correctly, this has also a high performance impact because you already have heard like 72 random bits are added and this and this. So overall we need 136 random bits per Gaussian sample candidate, and that results in a high randomness demand. So let's say on average we need 1.3 million random bits for a HT2 signing. And that's where we come back to the 85% of signing time. And what's more important is that 60% of signing time, so 60% of signing time, not of the hyperbole sampling time, is just used for generating randomness for the hyperbole sampling. And I think that's not only bad news, it's also good news, because once we have at some point Ketchak acceleration, this will shrink a lot. Yeah. So as of now, I'd say, or no, I'm pretty sure that HT will profit of Ketchak acceleration way more than dilithium does. Then slight topic cut here because I want to cover some other aspects as well. So our paper not only comes with a reference implementation and a VX2 implementation, we also have an ARM implementation. And as I said before, we have a 16-bit modulus, and theoretically you can use it, and we also use it for stack optimization in our ARM implementation. But it's actually not trivial to compute over 16-bit modulus, because already one addition can give you a carryout. And so what we're doing actually is we're recycling still a lot of the lithium code. So the NTT and large parts of the arithmetic are still borrowed from dilithium. It's working over 32 bits. So I'd say it's a first step, the ARM implementation, yeah, but there's definitely more potential optimizations to be done. And so performance-wise, we're actually between dilithium 2 and Falcon 512. Of course, this depends on your optimization variant that you use or that we would look at. But yeah, bearing in mind that for Hete, it's really the first round of optimization, and I think Dilithium and Falcon had like 3, 4, 5 rounds of optimization and different techniques there. So within most metrics, we're actually between Dilithium 2 and Falcon 512. And on a last note, that's also how I want to conclude the talk, is there's still a lot of room for improvements, and that's a bit of a pitch to the audience. So as I've already talked about a bit, is that the full potential of the 16-bit modulus is not yet leveraged. So in AVX2 and ARM implementations, we still use, for example, the Dilithium entity, and I'm sure, or I'm hoping that that's actually possible to use it a bit better, that we have a 16-bit modulus. At the very beginning of developing Hete, we actually also considered moving down to a 15-bit modulus. That's achievable, but that again then increases the signature size, and our goal was really, so our main goal was really to go for the signature size and public key size to go as low as possible. And so like performance might improve, but once you've settled down on a variant, on a specification, you cannot improve signature size anymore. And so that's the first big point. The second big point is the FFT. For our AVX2 implementation, we now use some intrinsics to somewhat optimize this FFT up to a certain FFT stage. But it's far from fully optimized. So I believe that with respect to the FFT cycle count, there is a potential for maybe even a factor 2 improvement still. And our ARM implementation has a non-optimized FFT, so no optimization whatsoever. There's a very high potential for speed-ups. And on a theoretical side, one thing that we also tried to solve, or we thought about a lot, is how can we do this hyperball sampling more efficient? Because that's really like, as I've told you, that's really like the most time-critical part right now. Yeah, it's a bit a pity. It's a bit a pity that there's many more things in the paper. Many more comparisons and implementation complexity and security considerations. So please have a look at the paper, and with that I conclude the talk. Thanks for listening. We're happy to take questions.
Any questions?
Hi. So you said that you were restricting the key space, actually, like you were doing rejection sampling on the keys. Did you compute kind of what the size of the key space is after that restriction?
That's a question for you.
So we've computed that we are keeping about 10% of the keys,
Okay.
which means that you can compute the key space with this info.
Great, thanks.
Yeah, I have a very naive question, so feel free to laugh at me if it does make sense. But so you do this bimodal thing. I was wondering, can you maybe generalize this a bit? Because your ring has very nice automorphisms. Can you maybe, instead of just multiplying by -1 or 1, apply an automorphism or something?
This is something we thought at some point with Damien when we were doing the theoretical results that told us that hyperbole were nice. But actually, it does not bring anything. Geometrically, it's not nice enough, and except if you're able to have, I don't know, like an exponential number of different centers, which seem like way too much to be realistic.
Okay, thank you. And also on slide 8, if you can go. Yeah, so this one. So I was wondering, it probably doesn't improve anything, but like you could draw an even smaller circle inside this blue region, right? Because you want, in the end, your distribution to be independent of the secret. So you could be, if you're in the smaller circle, then don't reject at all, right? So you could maybe reduce the rejection probability a little bit.
So there may be different ways of doing it, but I mean, in the end, we have this theoretical lower bound on the size or the radius you can get, and it is. So it's not exactly achieved by hyperbole, because the lower bound has like dimension -1, and hyperbole is like dimension, but asymptotically it's optimal. So there's no really point in looking for better ways, because
As you say, you have a lower bound on the radius of some.
If your goal is to minimize the expected norm of z, we have a lower bound which says if you want to do 6 repetitions on average, the expected norm of z will always be at least this or that. And with the way we set the hyperbole and the rejection sampling, we are very, very close to that.
Okay. Yeah, we can maybe talk a bit more offline, but thank you.
Okay, thank you.
Do you have any more questions in the room? If not, then let's talk the speakers again. Okay, now for the last talk of the session, we have a paper called Impeccable Ketchak Toward Fault-Resistant Sphinx Plus Implementations. And the authors are Ivan Gavrilan, Felix Oberhansel, Alexander Wagner, Emanuele Strieder, Andreas Zanki, and Felix will give the talk, so go ahead.
Thank you. Okay, so in comparison to the previous 2 talks, I didn't bring a new signature scheme, but I brought hopefully a useful way to implement an existing one. And that is our Impeccable Ketchak, and it's meant for resilient Sphinx Plus implementations. And I'm giving this talk kind of on short notice, so I did what any good lazy person does nowadays. I asked ChatGPT to explain why we need hardware countermeasures for Sphinx Plus, or SLH-DSA as it's now also called. And turns out if you do that, you get a pretty generic explanation of what a fault attack is. So not entirely unhelpful, but also not the point here. But good to recap, like fault attacks can allow you to reveal secrets. So far, so good. Little interesting side note, if you ask it like, why don't we need hardware countermeasures, and you add a little like, it's a hash-based signature scheme, right? It will happily reply that like hash functions are inherently secure to fault attacks, and yeah. So I will best explain it myself, why we do need them, and it's because of a little thing called the grafting trees fault attack. And I'm not going to go into details, but I highly recommend that paper. Basically, some hash-based signatures are built on multi-tree constructs, and there, by faulting a value, you can graft your own subtree, which you can then use to forge signatures. And last year at CHES, there was this nice paper which concluded that like introducing a single random bit flip anywhere in the signing procedure, you don't really care where, it might already be sufficient to achieve a forgery. And that's why the Sphinx Plus team recommended hardware countermeasures in their proposal, and the new FIPS standard also mentions them with caution. So, I mean, the problem of bit flips is nothing entirely new. Like the safety research domain has been at this for decades, because you also can have bit flips due to radiation. So can we use their approaches? And I would say to a certain extent, yes, we can, because the hardening of generic circuits like state machines or memories is quite well understood. But then cryptographic primitives are also a bit special, right? Like we have hardly any possibility for consistency checks, and usually we have like wide state vectors, parallel processing, and so on. And I think this is a good point to shortly talk about CatChuck, but I guess I don't need to introduce it in a CHES PQC session. It's like this sponge function where you absorb a message and then you can squeeze out something, and it's built on these 5 permutations you see here. And it's also built on a 3-dimensional state, and that's basically our large state vector, and usually we have 1,600 bits there. So back to this slide, not only are cryptographic primitives special, fault attackers are also special, and they are best not compared to like radiation, which might flip random bits, but fault attackers might reverse engineer an implementation to find its weakest spot and then be highly precise when introducing faults. For example, with laser fault injection, as we can do in our laboratories. So in literature, there are some implementations for SHA-3 that are meant for more safety domain. And this means they are, for example, 99.99% secure to 1-bit faults. But for a security domain, would you really trust that an adversary doesn't find this 0.01%? Maybe not, and I'm obviously not the first one to have this thought, which is why this concept of impeccable circuits has been around, which is also where our paper borrowed its title. An impeccable circuit is basically the principle of having like a circuit F and then having a redundant circuit to that works on encoded data. So you encode your data and independently process it, and ideally you then have multiple bits you need to flip so a fault isn't recognized. And shortly recap coding schemes, like I'm mostly going to talk about Hamming codes, and there you multiply your input with some generator matrix G, which is made out of the identity matrix and some encoding matrix P. So you basically get your original data and you get some encoded redundant data. And you characterize coding schemes by these 3 numbers here: the length of a code word, the number of redundant bits, and then most important for this talk, the minimal distance between 2 code words. So how many bits differ between 2 code words. So we started with the research question of how can we design an impeccable circuit for CatChuck so that we know its weakest point and we maximize its security in terms of bit flips. So cautionary note here for practitioners, like no shooting at shooting at stuff with lasers. For now, I'm only talking about theoretical fault injection. But at the end, I'm going to talk shortly about real-world circuits. So if you paid attention, you might ask, like, is the weakest point of such an implementation not just the minimum Hamming distance of the code? And ideally, yes, that's the case, but kind of obvious that you need to take care when implementing so it stays that way. And for this, I brought a little example, and I'm not going to show you a circuit, although it might be kind of intuitive that errors propagate and accumulate throughout a circuit. But I brought like the mathematical representation of one because it's going to be useful later. And here, for example, we have the add constant step of an LED cipher, and there this principle of impeccable circuit has already been applied once. And I think here it's also straightforward to see that if we flip 1 bit, it corresponds to this column of a matrix here, which is then equivalent to just adding and basically flipping 3 bits in your output. So I guess that's also pretty intuitive. And that, I mean, doesn't yet mean that this is insecure, but it's just a way of seeing how errors accumulate. But that's also something that's been known, and there is this nice concept of active security, which is kind of the probing security equivalent to, or one probing security equivalent, where probing security is meant for masking, and this here is meant for fault injection. And basically this states like you have a circuit and you have an error with Hamming weight, of up to D, which basically means you flip up to D bits, and it's at the Dth order active secure if you either abort or you still have the correct output. And then similar as with probing security, we have some interference notions. Here they are called accumulation or non-accumulation. And here basically we have a circuit, we have D1 errors in our input, we have D2 errors in our intermediate values, and now we are guaranteed for non-accumulation that the circuit either recognizes this in the boards, or we at least don't have any more errors than D1 plus D2. And more interesting for this talk, strong non-accumulation, where we again have D1 input errors, D2 intermediate errors, and now we either abort or we have D2 errors at the output. So basically, you don't drag your input errors with you. So knowing that this has been around, we were able to refine our question to like, how can we design an impeccable circuit? So we connected two principles of impeccable circuits and active security such that the resulting circuit is active secure. And I'm going to shortly propose some methods on how we did this. And for now, I'm only considering like linear circuits, which is pretty straightforward. Like if we have just a circuit with functions f1 and f2, and we make it an impeccable circuit by encoding our input data and then having like modified functions f1 and f2, and then having a checkpoint s at the output. And if we write that down as equations, it's pretty straightforward to see like the output of one circuit is the input to the next, and so on. And if you have any errors, you might have some on inputs, you might have some on intermediate values, and so on. And for linear functions, it's easy to see that like it doesn't really matter what the input data is. The errors propagate independently from the input data. So like very, very basic stuff, writing it like this. But the interesting thing here is we can consider that this is encoded data. So it's easy to see that our output is like either correct or it's only faulted if the error is also a code word, right? Because you can only get from one code word to another by adding another code word. So moving to a bit more complex example where we also have nonlinear functions, which we need for cryptography. Here it's useful to recall this property of strong non-accumulation, where we have, as I said, D1 errors in the input and D2 intermediate errors, and we know that we have at most D2 errors at the output. And here we can again write it as a worst case assumption where the error is independent from the processed data, and this we will use later on. So with that, I finally have everything for our catch-up. And for this catch-up, we used this encoding matrix here. So we encoded lanes in 4-bit chunks. And that's just some implementation trick that's been used before, because if you were to encode entire lanes, you would need a 64 by 64-bit matrix, which is not that nice to put into hardware. But if you split it into 4-bit chunks, it's actually quite efficient. And the only thing that's really giving you a headache when implementing this is the key permutation, because it has an AND gate, and this is basically the only nonlinear operation here. So what we did here is we designed an impeccable AND gate for which we could prove third-order strong non-accumulative, And for the proof, you can check out the paper, but basically we showed that it's important to have a checkpoint at the input, so you know that the data there is correct. And then we were able to design it simply by finding a way to compute it on encoded data, by having an AND gate, and then these some correction terms y, and then doing a compression of all that, so such that it matches the original data. And with that, we already have almost everything we need for our run function. We can then prove that our key permutation is also third-order strong non-accumulative. P is only a reordering of code words, so that's pretty straightforward. Jota the same, it's only an XOR of a lane with a constant. And then rho and theta, they only require some modified matrices. Only is maybe the false word here, because I've shown that matrices are kind of tricky to implement here. But there again, we were able to do a security proof where we used these small tricks that I've shown you earlier, where we can write down some worst case assumptions for everything that's strong non-accumulative, And for everything else, we can do an exhaustive simulation of error patterns with relation to the encoding scheme. So we put the complete thing into hardware, and we used a high-speed Ketchak approach. So basically, we have a state register, and then we go through all 5 permutations within a single clock cycle. And the encoded Ketchak looks similar. You also have a state register and the 5 modified permutations then. And the only trick here is to share like the encoding, decoding logic between like the initial encoding and the decoding for the checkpoint. So straightforward. As I said, we put it into hardware. We did an evaluation of RTX7 FPGA parts and the NAND G45 process design kit for ASICs. And if you put it into hardware, it costs you around a factor 3.2 more hardware than a normal Ketchak. And your maximum clock frequency decreases by 50%. So I would say this kind of seems acceptable with relation to related work, but obviously that depends on your use case. And I put related work into quotes here because there is nothing really related, because as I've said earlier, there are some designs from the safety domain which are, but maybe, or not all designs are secure even against single bit flips, at least not for every corner case. Whereas our design should be secure against all bit flips of 3 or less patterns. And even if you flip 4 bits, the fault probability ranges somewhere between 25% and 1.5 times 10 to the power of -9. So that's quite a large value range. It is because these 25% are for the case where you flip 4 bits within an 8-bit code word. So then you have quite a decent chance to compromise the circuit. And the 10 to the power of -9 are for the case where you distribute like 4 random faults throughout the entire 1600-bit state. So I promised I would shortly talk about real-world fault injection, but to be honest, it's kind of hard to give any intuition there. So with real-world circuits, we have things like clock trees, we have research structures, so it's not really an issue to flip multiple bits at once. But the only like related work that could give some kind of intuition was presented 2 years ago at CHES, and they did a evaluation of laser fault injection on exactly these kind of countermeasures, and there they were not able to fault impeccable circuits that used a full redundant approach. So meaning you add an entire, like you have the entire state twice as we have, and you process completely independent from each other. But then to be fair, they also were not able to compromise a design where the Ketchak was just duplicated, but that might be more simply achieved with having like a dual beam laser, whereas ours should ideally not be compromised with a dual spot laser, at least not by targeting in the individual bits. So if you assume that you flip always multiple bits with a laser beam, or you could at least, then it's, and this is actually quite a realistic assumption, then it's hard to say which one is more resilient. So with that, I'm basically already ready to conclude my talk. So the question was like, now what's missing to get towards a fault resilient Sphinx Plus implementation? Well, obviously, I think Ketchak is the most critical part there, but you would still have to put it into a complete implementation, so a complete processor, which is also hardened. So you would have to evaluate that. And probably if you spend some hardware on your chip to put Ketchak into it, you might not only want it to be resilient to fault attacks, but also can have some kind of side channel countermeasures, which we didn't consider, because for Sphinx Plus, that's not so much of an issue. But the good news here is there were already some interesting talks at CHES here, how to achieve that. So with that, I'm at the end of my talk, and I'm happy to answer questions if there are any.
very good talk and a very important subject because Sphinx Plus is very, very vulnerable to these attacks. It has this unique feature that if you fault it, it creates a signature which still verifies as a correct signature, which is really weird. So you can't use that as a method to detect that someone has been playing with your signing operation. So to be clear, so these countermeasures are these error detection methods, so that if I design a module which is signing that, I know that someone is trying to attack me.
They are error detection, yeah. No error correction. If
So I get a signal, so I know how to abort. And also, so what's your guess? So it's not really about the number of bit flips, but what is the probability of like detection with this? So just like an estimate.
Sorry, probability of?
Detection on the overall process of creating a signature, if there's a random bit flip somewhere in, let's say, any gate or register.
It's really hard to answer this, to be honest, because like I think from other papers, like there have been papers that did like even 4-beam laser fault injection, but like there you also have a probability that you even flip a bit, which is the lower end of percentages. So you would have to factor that into like our information theoretic approach of how many bit flips you can have and how they must be distributed. And then you maybe arrive at some real world resilience, so to say. But again, it's hard to say because like I also did some lab work, or at least I know of lab work where you don't even achieve laser fault injection because the chip just
it's
shuts
really
down.
Really a unique target in the sense also that you don't need to target the fault. You know, it can be just any bit. That's crazy.
Yeah, that was also our approach where we said like maybe it's not sufficient to put Ketchup twice on there, but have like this approach.
So if there are no other, okay, I'll just put one more in. So there is an issue with side channel leakage. So the thing is that it is using the SKey seed master secret everywhere. So from one trace you can probably get like the master secret out or some bits from it. So in a way it's like exceptionally vulnerable to that too. So
yeah,
right.
Good point. Yeah.
All right, thank you.
Okay, I also still have a question. So. If I understand correctly, so you say you have a factor 3 overhead and you protect against up to 3 bit flips, right? So naively, if you just do the whole thing 3 times, you're also and then you compare that, you get the same output 3 times, then you're also protected against.
Yeah, that's true.
So is there why is your work better than this?
I wouldn't, to be honest, I wouldn't inherently say that it's always better. Like something I didn't talk about is CIFA. It's I think short for statistical ineffective fault analysis, and there our design has some drawbacks because like you basically have to abort the moment you recognize an error. And that can also leak information. Whereas if you have 3 redundant designs, or you do it 3 times over, you can just do the entire thing and then decide to return some trash data and then not have this information leakage. So there I would say this simple redundant approach has some advantages. Yeah, to be honest, I would like to see a lab evaluation or do a lab evaluation of this, but like the paper I've shown on laser fault injection, they also had the conclusion that it's not that simple to say if like this approach or a simple redundant approach is better in every case.
Okay, thank you. Any more questions from the room? Okay, so let's thank the speaker again and all the speakers of the session.
Thank you.
Yeah, that's it.